The technology industry operates on a high-risk paradox. Developers ship highly capable mass-market systems first and only consider the safety regulations after the fact. We have seen the consequences of a release and patch cycle before. In the late 1950s, a drug called thalidomide entered the global market as a mild sedative, bypassing rigorous clinical safety trials prior to widespread distribution. The resulting wave of severe birth defects forced a legislative correction known as the 1962 Kefauver-Harris Amendment. This law requires manufacturers to provide mathematical proof of a product's safety before it ever reaches the consumer. Today, artificial intelligence development operates almost entirely in that dangerous pre-1962 paradigm. Models are trained, compiled, and deployed to millions of users, with safety treated as an eventual goal rather than a prerequisite. We saw early warnings of algorithmic overreach in 2012, when Target deployed a predictive model that analyzed purchasing habits to identify pregnant customers, exposing deeply private medical realities to families before they were ready to share them. By 2014, Amazon scrapped an automated resume screener after discovering the algorithm heavily penalized applications containing the word women's. The system had ingested 10 years of male-dominated hiring data and hard-coded that first model treats these privacy breaches and discriminatory outputs as inevitable software bugs that can be patched later. In reality, they are deeply rooted architectural flaws. The danger scales exponentially when we move from isolated algorithms to massive data aggregation. In 2018, the fitness tracking company Strava published a global heat map of its users' running routes. While an individual's morning jog is harmless data, aggregating thousands of those routes in conflict zones suddenly mapped the exact patrol paths and layouts of highly classified military bases. Modern large language models represent the most complex version of this aggregation threat to date. An LLM is a complex neural network designed to generate text by predicting the next logical word in a sequence based on vast amounts of training data. This compression process absorbs latent human biases, personal identifiers, and medical records directly into the model's parameters. Personally identifiable information, or PII, refers to data that can uniquely identify an individual, while PHI covers protected medical records. The financial liability for exposing this aggregated data is staggering. For modern enterprise systems handling sensitive records, a catastrophic data breach can carry an average cost of over $36 billion, and these systems are highly vulnerable. Recent security audits show a near-perfect success rate for adversarial attacks attempting to force leading frontier models to bypass their own safety filters and leak restricted data. When an AI outputs a discriminatory decision or leaks a private medical diagnosis, it is operating according to the exact specifications of its training data. To understand why a machine discriminates, we have to look at how it learns language through a mechanism called word embeddings. Word embeddings are a technique that converts words into lists of numbers so a computer can process them. This architecture translates semantic relationships into exact mathematical geometry. Words with similar meanings are plotted closer together, creating measurable distances between concepts. If you take the coordinates for woman, add doctor, and subtract man, early models arrive at the exact coordinates for nurse. Because the system scrapes centuries of unfiltered text from the internet to build this geometry, it mathematically mirrors the representation bias embedded in human history. We can see this architecture at work by testing a modern frontier model, like Llama 2-7b, to see what associations it defaults to when prompted to list occupations. This chart shows the top jobs the model associates with women, heavily dominated by stereotyped roles like teaching and nursing. This second chart shows the jobs generated for men. The results immediately shift to rigidly traditional occupations, peaking at engineering and construction. This is the result of the 6-stage bias pipeline. This pipeline includes reporting, selection, temporal, in-group, label, and representation biases, a compounding chain of human errors that infects the training data long before the model is even compiled. An LLM's output is an unedited mathematical reflection of our own historical prejudices. Bias is a foundational feature of the architecture. This same architectural vulnerability applies to raw privacy and PII data leakage. Researchers expose this vulnerability using a technique known as LLM probing. Probing is an adversarial method used to analyze the internal states of a neural network to forcibly extract facts hidden within its weights. By feeding a benign prompt into the model, attackers isolate the hidden embedding state of the final token, containing unformatted mathematical knowledge. They then train a linear regression classifier directly on this hidden state, successfully extracting exact birth years of notable individuals straight from the parameters. Even if the external application refuses to answer a private question, the raw data remains mathematically locked inside the parameters, waiting to be extracted. This technical reality directly conflicts with strict global privacy frameworks like GDPR in Europe, CCPA in California, and HIPAA for healthcare data. These laws legally mandate strict control, tracking, and deletion of personal information. It is impossible to execute a GDPR right-to-be-forgotten request when an individual's identity is dissolved into billions of interdependent neural weights. You cannot simply delete a specific memory from an LLM. Deploying foundational models under current architectural standards creates an irreconcilable collision with modern privacy laws. If human supervision cannot possibly scale to audit trillions of parameters, how do we secure these systems against data extraction and bias? The industry standard has largely been post hoc filtering. Post hoc filtering is the practice of bolting a separate safety filter onto the end of a finished model to block bad outputs right before the user sees them. Legacy filters fail against adversarial red teaming. Here, an older model gives dangerous advice, flagging the violation only after generating the text. Overfiltering causes clumsy refusals of safe queries. Conversely, a properly aligned model handles conflict constructively, offering safe guidance without breaking guardrails. Achieving that level of nuance traditionally relies on reinforcement learning from human feedback, or RLHF. Human raters grade outputs to teach preferred behaviors. But this manual grading is simply too slow and expensive to keep up with developing frontier models. To truly secure these parameters, the defense mechanism must scale at the exact same speed as the AI itself. It requires a machine-driven solution. The structural solution to the scalability problem is constitutional AI. It uses another artificial intelligence, rather than humans, to evaluate and correct the model. This is known as reinforcement learning from AI feedback, or RLAIF. In this architecture, developers first attack a baseline model with red teaming prompts. Then, a separate AI evaluates those toxic outputs against a rigid ethical constitution. It generates safe revisions, allowing a preference model to mathematically reward compliant behavior across the entire neural network. This creates a self-aligning engine, mathematically forcing the model to respect demographic parity and privacy boundaries internally before it ever interacts with an end user. Constitutional AI moves the industry away from reactive, post-deployment patching. By implementing proactive structural security, developers finally close the deploy first loophole and engineer bias directly out of the architecture.